this series of videos, we'll discuss section 7.3 of Stewart's textbook, Trig Substitution. And right at the start, I want to say that lots of students find this to be one of the most difficult topics in Math 2B. And the reason isn't because the new calculus ideas are so complicated, but this subject requires you to remember a bunch of trigonometry that you maybe haven't thought about in a while. So don't worry, we'll go over it in one of the next few videos, and we'll give a bunch of examples that'll help you to understand what things are important to remember. So let's start with what is the idea of trig substitution. So we're going to take an integral that has no trig in it at all, and we're going to substitute x equals some trig function. Maybe it's sine of theta, maybe tangent of theta, maybe secant of theta. And introducing this trig function is actually going to give us an easier integral than the one we started with. So for most integrals, the idea of substituting x equals some trig function is going to make your integral much, much, much more complicated. But in a few special cases, when you do this kind of substitution, you get a lot of nice simplification, and your integral gets much better. So the main idea is to substitute x equals some trig function. So trig substitution is kind of like U substitution, but there's an important difference that I'll talk about when we do our first examples. And this technique works really well when your integral has one of three different types of expressions in it. Something like the square root of a squared minus x squared, or the square root of a squared plus x squared, or the square root of x squared minus a squared. So we'll treat each of these three different expressions as a different case, because each one requires a different substitution. In this first video, I just want to show you a first example in case 1. We'll come back to case 1 again in the next video, and then we'll move on to cases 2 and 3 in further videos. So a first example. Let's take the integral from 0 to 1 of x squared divided by square root of 1 minus x squared dx. That definitely is something from case 1 where a equals 1. We have a square root of 1 minus x squared in the denominator. First, up to this point, when you have something like square root of some function inside, you might have thought, well, let's try U substitution. If you let u be equal to 1 minus x squared, then du equals 2x dx, but we have an x squared dx. So we're going to have an x that we can't rewrite in terms of u in any nice way. So U substitution does not work well here. So let me just show you the substitution that does work well. So let's let x equal sine of theta. So what's different here? Remember, when we did U substitution, we set u equal to some function of x. But here, we're setting x equal to some function of a new variable. So it's kind of like the reverse. Like instead of letting x equal some function of, instead of letting u equal some function of x, now x is some more complicated function. So everywhere we see an x, we're going to put in a sine theta. And just like in our examples with U substitution, when you substitute the variable x, you also need to know now what is dx in terms of d involving this new variable. Well, by definition, it's just you take the derivative with respect to the function on the right-hand side and then d theta. So in this case, we have something d theta, and our something is cosine theta d theta. So why is this a good idea? So I'll show you part of the simplification here. Now, in the denominator, we have a square root of 1 minus x squared. And that is a square root of 1 minus sine squared theta. But what is sine squared theta? What is 1 minus sine squared theta? This is cosine squared theta. So we have a square root of cosine squared theta. So let me say the first thing that people maybe find a little bit confusing. When you have a function like cosine squared theta, the square root is some function where you square it and you get cosine squared theta. So there's actually two functions like that, cosine theta and negative cosine theta. But for the purposes of this course, you can always write the square root of cosine squared theta as cosine theta. So why did this substitution help us? Because when we put in sine theta for x, what we get out instead of something involving a square root is just cosine theta, something that has no square root at all. So I'll pause and erase and then rewrite this integral, and we'll see the other cancellation and simplification that we get. When we let x equal sine theta, things already start to look better because the square root of 1 minus x squared now simplifies as cosine theta, something with no square root in it. So we rewrite this integral. Where we see x squared, we can now put in sine squared theta. Where we see square root of 1 minus x squared, we can put in cosine theta. And where we see dx, remember we said that dx is cosine theta d theta. So what happens here is the cosine in the denominator cancels with the cosine that comes from the dx. But this is not quite done, because we started with a definite integral from 0 to 1, meaning x goes from 0 to 1. And now we have an integral in terms of theta. So we need to adjust the endpoints. It's just like what happened in U substitution. So the question is, what is theta when x equals 0? So what is theta when x equals 0? And then the same question for the top endpoint, what is theta when x equals 1? Well, you know x equals sine theta. So if 0 equals sine theta, theta equals 0. So the lower endpoint is 0. The same idea. What is theta when x equals 1? If 1 equals sine theta, we pick the simplest value we can for theta, which is pi over 2. So remember, if x is equal to sine theta, then what is theta in terms of x? It's arcsine of x. So we have an integral from 0 to pi over 2 of sine squared theta d theta. So I'll just rewrite that to make this as simple as possible, sine squared theta d theta. And now how do you do this integral? Well, this is something we talked about in the last set of videos in the section 7.2 on trig integrals. Remember from last time, 7.2, that sine squared theta is equal to 1 minus cosine 2 theta over 2. So how did we compute the integral of sine squared? Is with this substitution. So we have, not a substitution, with this identity. So we have the integral from 0 to pi over 2 of 1 minus cosine 2 theta over 2. But let me just pull the 1/2 out here. 1 minus cosine 2 theta d theta. And what is an antiderivative here? Let me just rewrite this as 1/2 integral 0 pi over 2 of 1 d theta minus 1/2 integral 0 pi over 2 of cosine 2 theta d theta. We know an antiderivative of the first part is just theta over 2. Theta over 2 from 0 to pi over 2 minus, well, you could do u substitution here. Let u equals 2 theta. Then du is 2 d theta. So we're missing a 1/2. So an antiderivative here is 1/4 sine 2 theta, just like we saw in the video, 0 pi over 2. And the very last piece is now you have to evaluate these antiderivatives at the top endpoint minus the bottom endpoint, FTC2. So we get is pi over 4 minus 0 over 2, okay? And then minus 1/4 sine of 2 pi over 2. Sine of pi is 0. And then minus minus plus, another sine of 0. So what we get is pi over 4 minus 0 minus 0 minus 0. So in the end, what we get for this integral is just pi over 4. So remember, when we did u substitution, when we did indefinite integrals, at the end, you rewrite your integral in terms of x as an integral in terms of u. You get an antiderivative in terms of u, and you have to substitute back to get something in terms of x. But when you have a definite integral, what you're looking for is just a number. It's an assigned area under the graph of a function. So here, with trig substitution, it's the same way. When you're doing an indefinite integral, you have to substitute back at the end. But here, with this definite integral, we have this step where we have to adjust the endpoints. But that means that in the end, we just get a number. So our final answer is the integral from 0 to 1 of x squared over square root of 1 minus x squared dx is pi over 4.